Throughout my career of 4 years, I have failed interviews at Goldman Sachs and Fidelity, and then passed interviews at Microsoft, Amazon, and Adobe. Hello everyone, my name is Rajat, and I am a former HD at Microsoft. In this video, we will solve some DSA case studies problem, which will help you crack some of the top product-based companies. So without any further ado, let's get started. So let's talk about the agenda of the session today. So we'll start with solving a DSA case study problem, which is designing browser history. Once we have solved this problem, we will get a very good understanding of how to go about solving a DSA case study problem. Then we will create a blueprint of how can you solve other DSA case studies problems similarly. And then I will give you some homework that you can do after this class. So let's start with our first topic, is solving our first problem, which is design browser history. Let me explain you the problem statement. So the problem statement is, all of you have used browsers in your life. Any browser like a Chrome browser or a Edge browser. In every browser, the browser looks like this. Chrome, there is this search bar, and on the left side of the search bar, there are these two buttons, the left arrow button and the right arrow button. So the case study problem says that we have to design these two buttons. So you have to design the visit functionality, or what will happen when you visit a specific URL, what will happen when you click the forward button, which is this key, and what will happen when you press the backward key, which is this key. This is the problem statement that you have to work on. Let's take an example to understand the problem statement. So let's say you visit a link called LeetCode.com. So then you have visited LeetCode.com. Then you go to the next link, which is, let's say, gfg.com. Let's say then you visit a link bosscoderacademy.com. Okay. Now you go backwards. You press the back button. So now you go to the back link. Then you again press backward, then you go to LeetCode.com. If you now press forward, you go to geeksforgeeks.com. This is what you have to create and write code for. Now, since the problem statement is clear, so the first step is to understand the edge cases for the problem statement. So the step 1 is understanding the edge cases or scope of the problem. So for example, you can ask interviewers some questions on based of this problem statement. For example, the first question can be, can I open another tab as well? For example, in a Chrome browser, you get these different tabs. So, and there is a plus button here. If you press on the plus button, you goes on a different tab, then a different tab, then a different tab. And each of the tab has a separate backward and forward functionality. So in this problem statement, you have to not concern about this. There is only one tab possible in the browser. Another question that can come to your mind is that, let's say if I am at a link LeetCode, then I am at the link Insta, then I am at the link GFG, then I am at the link Bosscoder Academy, and then I go back, and then I go back, and then I visit another link, let's say FB, or I visit another link, let's say Hacker Earth, and then I go back, and now I again go back, and now I go forward, and then I again go forward. So let's say if I at Insta, then where should I go? Should I go to GFG or should I go to FB? Right? So the problem is that you have to go to GFG and remove all of this. Remove this from the browser history. Make sense? This is also one important case that you have to remember. Now the third thing is, what happens if I am at the last link and I press the forward button. So for example, let's say you are at LeetCode, then you go to Insta, then you go to GFG. You are at this and now you press the forward button. So what will happen? The question says the forward should be disabled. If you are at the last link, nothing should happen. Similarly, if you are at the first link and you press the previous, that is backward, then nothing should happen and this should be disabled. Right? Asking these follow-up questions will help you understand the problem statement very well. Now with step 1, you know the problem statement. So let's move to step 2 towards solving the problem. And let's take the first approach. The approach 1 that is coming in my mind is, let's solve this using a single stack. Why a stack? Because it looks like that you are storing elements in a stack. Let's say there I first visited LeetCode. Then I put LeetCode in the stack. Then I visited FB. Then I put FB in the stack. Let's say then we visit Geeks for Geeks. Then we are putting Geeks for Geeks in the tag, right? In the stack. So this looks like we are putting things in the stack. That's why stack comes in my mind. Also, stack is used in recursion and this looks very similar to recursion. That's also I choose stack as my first approach. Now, let's see if we can work it around using a single stack. So of course, visit is working fine. Now let's say if I go backwards, then what will happen? So I have LeetCode, I have FB, I have GFG. Now to go backward, I will remove GFG from stack. I will remove this and I will move backwards on FB. Makes sense? This is also working. But now let's say I want to move forward. Then what will happen? Now I can't move forward because I have already removed GFG from the stack. So I can't move forward. So this approach will not work. So I have to think of something else. So approach 2 that comes in my mind, which is follow-up of the approach 1, is the problem I was facing with approach 1 is that I can't go forward. I have deleted those elements which were in the stack 1. So the approach 2 is, let's use a 2 stack approach. Instead of 1, let's use 2 stack. Approach looks something like this. Let's say I have 2 stacks, stack 1 and stack 2. Let's say I visited LeetCode. So I will include LeetCode in stack 1. Let's say I visit FB, then I will push FB to stack 1. Let's say I visit Bosscoder Academy, then I visit Bosscoder Academy in stack 1. Let's say I visit Geeks for Geeks, then I will input Geeks for Geeks in stack 1. So this looks something like this: LeetCode to FB to BCA to GFG. Right? Now, let's say I move backward. Then what will happen? I will remove GFG from top and insert GFG in stack 2. I will remove GFG from top in stack 1 and insert GFG in stack 2. So I will input GFG in here and then I reach to BCA. Now let's say I again go backward. So what will I do again? I will again remove BCA from top in S1 and I will insert BCA in S2. So I will remove it from here and I will insert it in stack 2, right? So I now move to here on FB. Make sense? Now let's say I want to move forward. Then what will I do? I will pop from stack 2 and then insert in stack 1, right? I will remove DCA from top of stack 2 and insert DCA in stack 1. So I will remove it from here and I will insert it here. So now I have reached again to DCA and it's working fine, right? You can also do visit, you can also do backwards, you can also do forward. Great. Looks like we have solved the problem, right? Let's see if we have really solved the problem or not. However, before that, let's use a very important observation here, which is very, very important, is if you see that while you are maintaining these two stacks, the current element, the URL that you are currently at is always at the top of the linked list, is always at the top of the stack. So this is very, very important consideration, that your current, by current I mean current active URL, is always at top of stack 1. This is very important consideration. Let's see this again with a very small example. I have stack 1, I have stack 2. I visit LeetCode. So I am currently at LeetCode. So what is current at LeetCode, and it is at top of stack 1. Let's say I visit FB. Then current is at FB and on the top it is FB. Let's say I visit Geeks for Geeks. Then again current is Geeks for Geeks and Geeks for Geeks is on the top. Let's say I move backward. Then I remove from stack 1, insert in stack 2 and I move to FB as the current element. Then again FB is at the top of stack 1, right? Makes sense? So this is a very, very important consideration. Okay, makes sense. Very good. This looks good. Now we have to just think of that important case that we talked about in the earlier. The case was this case, right? That what happens when there is branching in the links and we have to remove from the browser history. Let's see if our code is working there or not. So let's see that. Let's create two stacks. Now let me explain this with an example. Let's say we visit a link A. Then we will insert this in stack 1. Then let's say we visit the link B. So we will insert in stack 1. I am creating in parallel how this looks as well. Now let's say I do visit C. Then I will insert C here. Now let's say I go backward. So what will I do? I will remove C from stack 1 and insert C in stack 2. So I will delete from here and move C to stack 2 and now I am at B. Now let's say you visit D. Now since you are visiting D from B, you should remove all the elements which are here on the right side of B because they will now no longer be part of the browser history according to the problem statement. So before inserting D in stack 1, you will first empty stack 2. If there are any elements, if there are even 10 elements in stack 2, you will empty it and then insert URL or D in stack 1. So you will first delete C and then insert D in stack 1. And then the things will go similarly. Okay. Now let's write the code for this. I am here writing a pseudo-code. So let's create two stacks. stack let's write the visit function. The visit function will return a string and take in a string URL as an argument. So first thing is, if there are any elements in stack 2, then we have to first empty the stack 2, right? So, and then once we have emptied the stack 2, then we will insert in stack 1. So let's write this. So we will empty the stack 2. So we'll do if s2 dot is empty is equals to false. Rather than if, we will use while stack 2 is empty is equals to false, we will keep deleting popping element from stack 2. This will empty the whole stack 2. Now we will insert in stack 1. So we'll do stack 1 dot insert, and then we will return the stack 1 dot top, which will return the top element of the stack. Okay, now let's write the forward function. Forward function will return a string and will not take any argument. So we will check if we are at the last link, then there is no forward path, right? Otherwise, we will remove top element from S2 and insert this element in S1, right? So if S2 dot is empty is equals to true, that means the S2 stack is empty. That means there are no elements that we can go forward to. Then we will just return null, or we can return the current element itself, which is stack 1 dot top. Otherwise, we will remove the L from the top element of S2. So we'll do string element equals to S2 dot pop, and then we will insert this element in stack 1. Stack 1 dot push element, and we will return stack 1 dot top. Now, how will the backward look like? Again, it will return a string but not take an argument. We will again check if we are at the first element, then we will do nothing because there is no backward path available. Otherwise, we will remove top of stack 1 and insert in stack 2, right? So let's see. So if the stack 1 size is right now 1, that means that I am at the first element. Then I will return either null, or I can just return stack 1 dot top, the current URL we are at. Okay. Otherwise, we will remove top from stack 1, which is string URL equals to stack 1 dot pop, and we will insert in stack 2, stack 2 dot push URL, and then we will return the stack 1 dot top, because stack 1 dot top is always the current element which we discussed earlier. Now let's see the time complexity of all the approaches. For backward, the time complexity is, of course, order of 1. The time complexity similarly for forward is also order of 1. But what is the time complexity for visit? In worst case scenario, this loop can go n number of times. So the worst case time complexity for visit is order of n. So this will be order of n. So this is a correct approach, but not an optimized approach. This brings us to our third approach, which is a doubly linked list approach. So in a doubly linked list approach, each URL will be part of a doubly linked list. So let's say I visit LeetCode. Then I will create a doubly linked list by LeetCode, which previous and next will be null. Then let's say I visit Facebook. Then the LeetCode's next pointer will point to FB pointer. And the FB's previous pointer will point to LeetCode's pointer, and these two will be null. And this will be the current pointer, because I am at right now here. For this, current will be here. Now let's say if I visit another link, bosscoderacademy.com, then I will be at LeetCode, then this will reach to FB, then this will reach to Bosscoder Academy. Go here, this will go here, this will go here, and now my current will be here. If I want to go backward, then I will just change the current to here. If I want to go forward, then I will change the current to here. Right? This is what we have to do. Let's start thinking about how we can do this. So first, once we do the first visit of LeetCode, let's say, or maybe let's say visit of a link A, then we will do a simple thing. We will first create a new node whose data will be equals to A and whose next will be equals to null and previous will be equals to null. And the current pointer will point to this new node. So simply you have a new node which you have created whose data is A, previous is null, next is null, and the current pointer is pointing to this node. Now if I do another link, visit B, then how things will work? I will again create a new node whose data will be equals to B and next and previous will be equals to null, right? So now I have A, and current is pointing to this, and now I have a new node which is pointing to B whose previous and next is null. Now what I will do, I have to now intersect these two nodes, connect these two nodes together. So what I will do, I will do current dot next equals to new node, which is current's next will now point to where new node is pointing, and then I will write new node dot previous will point to where current is pointing. So I will remove this, and the current node previous will point to where current is pointing, and then I will update current to new node, that is current will start pointing to where new node is pointing. Make sense? This is how you do a visit in a doubly linked list approach. Let's do it for one more visit of C, right? Let's see, write the same algorithm. We first will create a new node whose data will be equals to C and whose next and previous will be equals to null, right? So now we have A, we have B, we have current pointing to B. Then we have a new node which is created, and this is pointing to C, whose next and previous is none. Now we will again write the same thing. We will write current dot next will be equals to new node. So the current next will point to new node. I will remove this, and current new node will point to where new node is pointing. Then new node dot previous will point to where current is pointing, right? So we will remove this, and the new node previous will point to where current is pointing, and then current will update to where new node is pointing. Just this. Now we have again connected them and updated the current. Now let's say if we go backward, then backward is very simple. We will just first check whether there is a backward path available. We can easily check it. If current dot previous is equals to null, that means I am at the first node, then there is no backward path available, so I will do nothing. Otherwise, what I will do, I will just do current equals to current dot previous. That means current will point to where current dot previous is pointing. Current dot previous is pointing here, so I will just do this, and I will just point this to here, right? Let's say I want to go forward, then if this is also very simple. I will just do if current dot forward is equals to null, that means there is no forward path available, so do nothing, and then just do current equals to current dot next, which is again very simple. I will just point current to where current dot next is pointing, so this will remove from here, and current will point to where current dot next is pointing. Very simple, right? Now let's just understand our important consideration as well, that whether we have to remove links. In that case, how this will work. So now let's go one step more backward, and if we go one step more backward, we will reach here. A, we will just do current equals to current dot previous, and B is pointing to C, this, and current is right now. Let's say if I do visit now, visit of D, then what will happen, right? If I do visit of D, then what will happen? Of course, I will first create a new node where data will be equals to D, and where next and previous will be equals to null, right? So I have created a new node by D. Now I have to combine B and D together, right? So I will do current dot next equals to new node. With this, I have broken the connection between B and C. See, from this is now pointing to D, right? And now I will write new node dot previous equals to current, which is remove this, and this will point to this, and then I will write current equals to current dot next, or current is equals to new node, whatever you want to write, both are right. So then current will point to where new node is pointing, which is here. Current will point to here. Now if you go backward from here, then you will go to here, D. If you again go backward, you will go here. If you go forward, you will go here. If you again go forward, you will go here. So this is automatically removed. So this approach is totally fine, right? This is the doubly linked list approach. I think you can write the code by yourself. It's very simple. Just let's see the time complexity. In this backward, you are just going one step backward. It is order of 1. You are forward, you are just going one step forward. It is again order of 1. For visit again, you are not really looping in or deleting anything. So it will again be just order of 1. which is a much more optimized version of the previous approach. So this is a right optimized approach for this problem statement. Now let's conclude our discussion. Let's create a blueprint of how you can solve a DSA case study problem. Like you see the design browser history problem, the first step is to ask clarifying question. To understand the problem statement efficiently. Then come up with approach 1 and see whether this is working or not. Then come to approach 2, approach 3. And at each step, talk about which data structure you will use. Why you are using this data structure and how will the implementation look like. And also discuss the time and space complexity. And based on the time and space complexity, try to optimize the solution and come to the final solution. This is how you solve a DSA case study problem. Now let me share you 2 important homework questions that you can practice after this class. The first problem is design Facebook networking system. And the second problem is design Instagram Reels system. Try to understand these problems, how the Facebook networking will look like and how the Instagram Reels scroll will look like. With that, thank you very much for attending the masterclass. So this was it for the video. I really hope you find this DSA case study video helpful. So if you like this video, do like, share and subscribe to the channel. Until we meet again.